So an alternative to using the ICE table is to use a systematic approach. So if we do an example, let's say we want to find the pH of 0.15 molar ammonia solution, ammonia being a weak base. So we have a couple of equilibria involved here. Ammonia as a weak base will tend to accept a proton, and it'll come to equilibrium, so you get ammonium NH4 plus and the hydroxide ion. You've also got autoionization of water. Before I do that, let's just put in the K value, or the K expression. This is the B, so it's a base dissociation. It's going to be the equilibrium concentration of ammonium multiplied by hydroxide over ammonia. We also have the autoionization of water. So water acting as an acid and a base, so it can accept a proton to become ammonium and lose a proton to become hydroxide. And the K for that is called Kw. We ignore the water in both these equations because it essentially doesn't change. So this will be the concentration of HO plus times OH minus, which we know is 1 times 10 to the minus 14. The value of Kb is 1.75 times 10 to the minus 5. Just happens to be the same value as the Ka for acetic acid. That's purely coincidence. So we have 4 unique chemical species which have unknown equilibrium concentrations. There's ammonia, ammonium, and we also have the hydronium and the hydroxide. So we need 4 equations. We have 2 at the moment, the Kb and the Kw. So we're going to add the mass balance equation and the charge balance equation. Mass balance equation just says we don't make atoms or destroy them. So our initial concentration of ammonia, the ammonia is converted into, either stays as ammonia or it's converted into ammonium. So those equilibrium concentrations added together must equal the initial ammonia concentration. And we can also do a charge balance, and this says that all the negative charges have to be balanced by the positive charges. So the only negative charge we've got here is hydroxide, so that has to equal the ammonium plus the HVO plus. In this case, they're all +1 or -1 ions, so they will essentially multiply by 1. If you had 2 plus, you'd have to multiply the concentration by 2. Okay, we can make a couple of assumptions here. Because this is a basic solution, we can say that the hydroxide concentration is going to be much greater than the HVO plus, and therefore essentially the OH minus concentration is equal to the ammonium concentration. Another kind of approximation we can make is that since the Kb value is very small, very little of it is going to make NH4 plus this stuff. So that's going to be small. So we can say that the concentration of ammonia at equilibrium is going to be much greater than the concentration of ammonium. And so we can essentially get rid of that. And we can just say that the equilibrium concentration of ammonia is approximately equal to the initial concentration of ammonia. Okay, we now have 4 equations for 4 unknowns, so we can go ahead and solve. So what we're going to do here is we can say that our Kb expression which are the products for the base dissociation, so ammonium and hydroxide over ammonia. What we're going to do here is say that since ammonium and hydroxide are approximately equal, that was one assumption we made, that this is equal to OH minus squared, and we said that the ammonium at equilibrium is approximately equal to the initial. So we'll just rearrange. So we get the OH minus concentration equals Kb times the initial concentration of ammonia square rooted. We have those values. We know they're 1.75 times 10 to the minus 5. Initial concentration we said at the beginning was 0.15. We'll square root that. Get an answer of 2.63 times 10 to the minus 6. If you take the negative log of that, we get the POH. So take the log, make the value negative. We get 5.58. 14 minus the POH equals the pH. So the pH equals 8.42. And that makes sense because it's greater than 7, and we know it's basic.